today and I think on Friday, what we're going to do is just do basic, pure math point set topology. Now, I want to try to give a bit of intuition of why it makes sense to talk about these things, right? Because the definitions and the theorems and so on, you can easily read off the book and just work out the proofs yourself, which I think is a great exercise. But what I'll try to do too is give you some intuition of why it matters, right? And why one should abstract and so on, right? So we want to be able to talk about smoothness of functions, right? And in particular, we want to be able to say that a function is, say, differentiable around a point, right? Because then if a function is differentiable around a point and say the derivative is 0, then the function needs to be, say, constant, right? We want theorems of this style, right? But for this, if we have a point, we need to be able to argue that the function is smooth or differentiable around it, right? And what do we mean around it, right? It doesn't matter how, it's not like you need to behave nicely at every point at distance 1 or minus or smaller than 1 or anything like this. All you need to do is to be able to zoom in and see something that contains a ball, right? Because then you can just zoom in, work in that ball, and you can do everything, right? And so in this notion of ball and zooming in and points being closed, and even if we want to talk about convergence and so on, we need some notion of what is near, right? We need to know what is near and what is far. Right? We need to have a notion of how do we talk about things being near and far, and for this we need a distance. Right? Or in math, we call this oftentimes a metric. Okay, and so what do we need this metric to satisfy? Okay, so if we have a metric space, what we would like to satisfy? So usually the way we do things is we define things with axioms, and then, right, we prove theorems that confirm that these axioms were well designed to start with, and they correspond to objects that we care about and that we're familiar with. Okay, so for example, right, so let me write an example. So an example, the distance between a point x and y, both over the complex numbers and the imaginary numbers, could just be the modulus of x minus y. That's usually the distance that we care about, right? Or they could be, the L2 norm if we are in Rn or even in Cn, right? But now if I have two functions, defining a distance between functions starts being a bit less clear, right? But one can, of course, still do that. Okay, so what we would like out of the distances, we would like it to satisfy 3 axioms, right? So it should be that the distance between 2 points is 0 if and only if the 2 points are the same, right? If 2 points are the same, the distance should be 0, and if the distance is 0, then the 2 points should be the same. Right, now property 2, the distance between x and y should be the same as the distance between y and x, and of course triangle inequality. Right? If I have to go from a place to another, if I force myself to go to make a detour, it should only take me longer. Right? So d xy dissolve for all x and y, right? For all x and y in the metric space, x and y smaller or equal to 1. Right? If I go from x to z and then from z to y, it should take me longer than if I go straight from x to y, right? In any good notion of distance. Okay. And now, there's other things that we would like the distance to satisfy. Right? For example, we would like the distance to be positive. Right? If distances are negative, then it's sort of a very strange thing. But this comes out immediately, right? Because from property 3 and property 2, right? Property 1, sorry. Right? Because if I take y equals x, right? If I do this with y equals x, maybe I should write z here so that it's easier to see the substitution. If I do it with y equals x, I get dxx is smaller or equal than twice dxz, right? But I know that this is 0, right? So this needs to be bigger than 0. Okay, so from those 3 axioms, you can already get this. Okay, so now a few definitions. Okay, so now that we have a notion of distance, we can talk about balls, right? So a ball around a point of a radius delta is just a set of points whose distance is smaller than delta. So just a set of points, say y, such that distance between x and y is smaller than delta. Okay. Now we say that, right, so this is the notion of a ball, right? The notion of a neighborhood. Right, we want to be able to talk about sets where you know the point where I can zoom in on the point and I can find a ball that's inside the set. This is exactly the notion of a neighborhood, right? So n inside the metric space M or S, or use the word S, right? Is a neighborhood. Is a neighborhood of X if there exists delta such that the ball of X delta is inside M. Okay, so if for a point I can find a small ball that is still inside the set, then I say that the set is the neighborhood. All right, and now we can talk about open sets. I'm sure you've seen a lot of this in real analysis. An open set, so like say a set S is open, so S is an open set. I don't need to be inside of anything. Okay, let me just, there's no need. Is an open set if S is a neighborhood of lowest points. And open sets are sort of the most important thing, right? Because if a set is open, it means that for any point in the set, I can talk about what it looks locally around that point, because there is a ball inside that point that is still inside the set. Okay, now closed is exactly the opposite, in the sense that, not in the sense that it's not open, but in the sense that S is closed if the complement of S, okay, so this is what we use, so not in S, right? All of this is inside some metric space M, right? Some ambient space, right? It's closed because S is open. Okay. So open is important because it allows us to understand, and around any point it makes sense to understand local behavior around a point. Closed is important because it means that the outside of the set is open. So in particular, a closed set will be important for things to converge, right? Because if I have a sequence having some kind of limit, right, then it's not so hard to see that the limit will have to be inside the set if it's closed, right? Because if it was outside the set, then because the outside of the set was open, I could make a ball around it that would not intersect my set, and therefore my sequence would never go inside the ball, and so it wouldn't be a limit, right? We'll do this a bit more carefully. Okay, now a few more definitions, and then maybe I'll show you the proof of a theorem or two, just for you to see the kind of arguments they go into play. Okay, maybe I'll leave. That's fine. Okay, so basically what you need to remember, most important thing is that the set is open if for every point in the set you have that there exists a ball still inside the set that around the point. Okay, so a few more important definitions. Given a set X, the interior of the tilde S means complement. Yeah, okay, right. Maybe I should So tilde S means all sets, all points x, say, in some big space called M, right, the ambient space, such that x is not in S. Right, that's what I mean by the tilde. So now the interior of X will be the largest, open set S inside X. Okay, so this is known as the interior, right? So if I have a set, I can talk about the interior. Okay, why is this well defined? Because basically, if I have, this is well defined because the union of open sets is open. Right, so the union of open sets is open. Right? And so basically the interior, I can just define the interior of X as the union of all open sets, say S open, such that the union of sets is that S is open and S is inside of X. Right, so there is such a thing as the largest closure, right? Because if there was something that wasn't contained, any open set was not contained in the interior, then I could just take the union with that. Right, so every open set is inside the interior of X. Okay, now the closure, we call X with a bar like this, or sometimes closure of X. It's sort of the dual to this in some way. So it's the smallest set S that is closed, and X is contained in S. Right? So exactly for the same reason, like intersections of closed sets are closed. Right, because you can just think, right? They're complements of open sets. So if unions of open sets are open, then intersections of closed sets are closed. And so this is just the intersection of all closed sets. Same thing. Right? Set is equal to the intersection of all S closed in S. S now needs to contain X. Okay, and so in particular, right, X is inside its closure and contains its interior. Right. And so. Right, and so now, basically with the set X, you add a bit more for its closure, right? You're basically adding all the limit points. And now you take away a bit for this interior, right? So you're adding only the points that have balls around it. And sort of everything in between is called the boundary. Right, so think of a ball, right? Think of, like a ball, right? The thing not counting to the boundary is the interior. Right, the closure will be counting if you count the boundary, it will be the closure. And so you would like to say that exactly what's in the line is the boundary of X. Okay, so we'll define this. So the boundary of X. So boundary of X. Right, so the boundary of X is given simply by the closure minus the interior. Right, so every point that's in the closure, but is not in the interior. Okay, so in particular, right, maybe a good thing to see is if X, so if a point X is in the boundary of big X, then, I mean, it may or may not be in X, right? If X is open, that's exactly equal to its interior. If X is closed, it's exactly equal to its closure. But in general, in the boundary, it could be in or outside. But in particular, for all delta, it must be that the ball centered in X and delta, with radius delta, intersects both the interior of X and the closure. And now, I'm sorry, intersects both X and X complement. Right, they are exactly the points in the boundary, right? That if I take a point and I look at a ball, it will always intersect, let's say this is X complement, will always intersect X and X complement. Okay, so I promised I would finish a couple minutes before, so let me finish. What we're gonna do next is talk about connectedness. So it's also what we're gonna wanna, just 1 minute, we're gonna want to define functions, right? Like in some, what we're gonna call region, right? So let's say a region like this. We're gonna want the region to satisfy a couple of things, that for any point we can zoom in and see a ball so that we can talk about locally what the function looks like. And also that we're gonna be able to draw lines in between any 2 points of the region. So we're gonna want the regions to be connected. And so next time what we're gonna talk about is connectedness. Right? When is it that a region is connected in the sense of topology? And someone asked, yeah, this is for all delta, of course. Yeah, sorry, wrong. For all delta or for all open set that contains X, or for all neighborhood even, right? For all neighborhood. Of X, right? All neighborhoods of X that intersect X and X prime. Yes, thank you. Okay, all right. So I'll see you all on Friday, and we'll talk about connectedness and see a few theorems. Topological definitions of connectedness, and that it corresponds actually to connecting lines and so on, just for you to see a feel of the kind of arguments that go into topology. Okay, and then we'll start talking about regions on which functions are smooth and so on. All right, thank you.